Now, this question is asked regarding the lanthanides. If +3 oxidation state is the common oxidation state, is there any other oxidation state stable for these lanthanide elements? This question is often asked. If +3 oxidation state is the common oxidation state for lanthanides, what about higher and lower oxidation states? For example, which member of the lanthanide series will exhibit a lower oxidation state? For example, you are familiar with europium, ytterbium, europium. Probably you are aware of the fact that gadolinium is the central element in the lanthanide series of elements. Before gadolinium will come this europium. Similarly, the last element in the lanthanide series is lutetium. Before that last element comes ytterbium. So, europium, samarium, these are capable of forming compounds in +2 state, whereas ytterbium similarly +2 state. So, not all lanthanide elements are capable of forming compounds in lower oxidation state. Similarly, higher oxidation state is also possible in the case of lanthanides. The first element, lanthanum. The next element is cerium. So, the element coming after the first element, lanthanum, cerium. Similarly, the element following gadolinium, they are capable of forming compounds in +4. And another interesting feature one can notice, one of the important properties in the case of periodic table discussion is plotting a graph. Similar elements occupy similar positions in the graph if you plot any property along with the atomic number plotted. Interestingly, it has been observed europium, ytterbium, if you plot a graph, say you consider atomic radius for example, you plot a graph connecting atomic radius and atomic number, you can notice for all the elements in the periodic table, this rule is applicable. Similar elements occupy similar positions in those graphs. Interestingly, it has been observed that europium, ytterbium, these occupy positions similar to that occupied by barium. So, if you plot a graph connecting radius versus atomic number, you can notice if barium occupies a position like this, in the graph you can notice a position occupied by europium, similarly a position occupied by ytterbium. You can notice the maxima, these positions are occupied by europium, ytterbium, and these positions are similar to the position of barium. So, a question like this may be asked. Europium, ytterbium, they form compounds in +2 states. You can notice in the graph they occupy similar positions, maxima, just like barium, which is forming compounds, stable compounds in +2 state. Therefore, if you plot a graph of any property of these elements versus atomic number, you can notice maxima, minima and intermediate positions in those graphs, and you can come to this conclusion that similar positions are occupied by similar elements of the periodic table. So, without knowing any chemistry, for example, depending only on the positions of these elements in the periodic table, to some extent we can predict the nature of compounds that are formed. So, this is the important point one can notice. Another interesting feature you can also notice, namely the lunar samples. Some of the lunar samples, they contain abundant elements. For example, a plot like this was observed. This is percentage abundance of the elements present in lunar samples, and this again illustrates this point. Positions of barium, europium, strontium. You can notice they occupy the minima in the graph as far as the abundance is concerned. Again, position of barium a minimum, europium a minimum, strontium belonging to barium group, and all these three occupying similar positions in this type of abundance graph in lunar samples. Another interesting point which I can mention here is this, namely I plot a graph again for atomic radius versus atomic number. If I plot a graph for these lanthanide elements, we again notice a graph like this. This is for barium, europium, ytterbium. As the atomic number increases, we find in the case of atomic radius versus atomic number plot, again as already I have mentioned, positions of barium, europium, ytterbium, etc. are found to be quite similar, indicating that europium and ytterbium chemistry similar to that of barium. Whereas if you plot ionic radius instead of atomic radius, you plot ionic radius, we notice for lanthanides this is the type of graph we find. Here the difference which we notice in the case of europium, ytterbium, that difference in the plot is not found here. From lanthanum 3 plus to lutetium 3 plus, there is a gradual decrease in the ionic radius. Of course, there are plots for +2 and +4 oxidation states also, but we find that some of these points, based on this, I think I can go in for a discussion of some problems.